Alright, welcome to our summative 2 review for some of the like multiple choice and free response options that kind of cover some of the topics that we have talked about in the second half of this unit. So I'm going to go ahead and do the I do problems, and then I'll give us some time to try the you do problems on the right side of our papers as well after I do my example. And so first we're looking at this first box here on the left. We have two functions, f of x and g of x. And it's asking me to find f following g of 3 for letter A. And so in this case, we have composition of functions. I always like to rewrite this as f of g of 3. So I can see, like, really obviously, what is my inner function and what is my outer function. I know that I always need to start with what is on the inside. And so that is going to be my primary focus to begin. G of 3. Which means I'm just plugging 3 in to g of x. So 3 squared is equal to 9. And what I'm going to do with that 9 is plug it in where I had g of 3. So now instead of doing f of g of 3, I'm looking for f of 9. And I can actually evaluate that now. Plugging in 9 for x and f of x, I get 2 times 9 plus 7. And that's going to give me a final answer of 25. And so f of g of 3 is 25. Now there might be some examples where we have f of g of x, right? It's not of a number, but we still have our x value in there. That means we're literally plugging in our inner function, g of x, in to f. And so I like to rewrite it as f of, and then actually replace what is going inside my parentheses here with what the actual function g of x is. So f of x squared. And then I'm going to just write out f of x, which is 2 times x plus 7. But every time I see an x, I'm going to leave a set of parentheses there instead. That's going to tell me, hey, what do I need to plug in here for x? I need to plug in x squared. Need to plug in x squared. And when I do that, I get 2 times x squared, which is just 2x squared, plus 7. And that is equal to f of g of x. And so those are the two primary examples we'll see. Composite functions with a number that we're actually evaluating at, and composite functions where we are just looking at a variable. And so I'm going to go ahead and give you the time to try the two problems that are on the you do side of our notes. Now we're trying to find the inverse of the given function f of x. I know my first step is to replace f of x with y, so I have y equals the cubed root of x minus 2 minus 3. And then the next step, step 2, that is like the biggest step that's actually applying what we know about inverse functions, is that we're going to be switching our x and y. So every time I see a y, I'm going to put an x. And every time I see an x, I'm going to put a y. So that I have x equals the cubed root of y minus 2 minus 3. And from here, my main goal now is to isolate y, to solve for y, because that is going to give me my inverse function. And so first I need to add 3 to both sides because I want to get my radical by itself. So I have x plus 3 equals the cubed root of y minus 2. In order to get rid of my cubed root, that means I need to cube both sides. So cube both sides, because it's a cubed root. There's a 3. I need to take each side to the third power, so that my root and this power cancel out. All I'm left with on the right side of my equation is whatever was underneath my radical, which is y minus 2. And then on the left side of my equation, I have x plus 3 cubed. The last thing I need to do is go ahead and add 2 to both sides so I can get y by itself. Y equals x plus 3 cubed plus 2. The last thing I need to do is make sure I'm actually being accurate with my notation, right? We already have some y equals. That's what f of x is. I need to replace this y with f inverse. So f to the negative 1, f negative 1 of x equals x plus 3 cubed plus 2. Again, I'm going to give you the chance now to go ahead and try the same very similar problem on the right side of our column here. Now let's go ahead and actually put both of these topics together in one problem. Right? We see our ultimate goal for this problem is to find and simplify this fraction. In our numerator we have f inverse of 7 plus 4. And in my denominator I have g of f of negative 7. I like to split my work up in this way because I think it helps break down the problem into more bite-sized pieces for us. So I'm not overwhelmed by this crazy fraction with a lot of things going on. I'm just focused on, like f inverse of 7. In order to find f inverse of 7, right, I can't just plug 7 in for f because that's not the inverse function. I'm looking for f inverse of 7. So I need to have my inverse function first. I need to find that, which we just did. Right? We're taking our normal function f of x, switching our x's and y's, so x equals the cubed root of y minus 1 plus 3. Go ahead and subtract 3 from both sides. So get x minus 3 is equal to the cubed root of y minus 1. Because we're taking the cubed root to cancel that out and get rid of it, we need to cube both sides, so take both sides to the third power. So I have x minus 3 cubed equals y minus 1. Is this the same? No, it's not. Super similar to the one we just did, but not quite the same. So that I add 1 to both sides, and I'm going to rewrite y as f inverse, so f inverse of x equals x minus 3 cubed plus 1. You will get points on this problem for having your inverse function. Part of the points come from this specifically. So if you don't have it, like, you're missing out. And if you don't have it, you're not going to be able to actually evaluate f inverse of 7, because now that I have it, now I can finally plug in 7. So f inverse of 7, I'm just plugging 7 in for x into my inverse equation. 7 minus 3 cubed plus 1. That's going to equal, let's see, 7 minus 3 is 4. 4 cubed is 64. 64 plus 1 is 65. And so f inverse of 7 is 65. But in my numerator, I'm looking for f inverse of 7 plus 4. So I'll take 65 plus 4. And that is equal to 69. That is going to be the numerator of this function here. I'll go ahead and write that in my third part of my work. So 69 divided by whatever g of f of negative 7 is. Well, we're going to start with our inner function, which is f of negative 7. So f of negative 7 is equal to the cubed root of 7 minus 1 plus 3. Oops, negative 7, sorry. Negative 7 minus 1, that's negative 8. The cubed root of negative 8 is negative 2. And then we add 3, and so f of negative 7 is positive 1. Once I have positive 1, I'm using that as my input for my outer function, so I'm plugging that into g, so g of 1. G was given to me as a graph, so I'm looking at an x value of 1, because that's 1 is my x value. Where is my function defined? It's defined down here at negative 5. So g of f of negative 7 is equal to negative 5. That is going in the bottom part of my fraction, and that is going to be my final answer. In this case, we can't simplify it all, but I would even accept an unsimplified answer if you chose to give me that. And so now I'm on a separate sheet of paper. I have another problem that's similar to this that we're going to take some time to do. All right, so I'm trying to find the domain of the following function. We talked about the fact that pretty much, most functions are going to have a domain from negative infinity to positive infinity, except for when two things happen. If we have a fraction or if we have an even root. In this problem, we actually have both, right? We have a fraction, the square root of x plus 5 divided by x minus 1. And I have an even root, this square root of x plus 5. The reason these are issues for us, and we have to really consider them when we're trying to think about what the domain of our function might be, is because first, for a fraction, we can never divide by 0. And because of that fact, I need to make sure that whatever I plug in for x does not make my denominator of this fraction equal to 0. So my denominator, which is x minus 1, I need to say it cannot equal 0. So an equal sign with a slash through it. X minus 1, my denominator, cannot equal 0. And when I go ahead and solve for x, I'm adding 1 to both sides. I get x cannot equal 1. And that makes sense, right? If we plug in a 1 for x, we get 1 minus 1, which is 0. So that's the math we just did. So x cannot equal 1. The second thing we need to do is, when we're thinking about an even root, like in this case a square root, we know that we cannot take the square root of a negative number because that would give us imaginary solutions. And so we need to make sure that whatever's underneath our even root is not negative. It needs to be greater than or equal to 0. And so that's exactly what I'm going to do. I'm going to set x plus 5, which is what was underneath my radical, as greater than or equal to 0. And now I can go ahead and solve for x by subtracting 5 from both sides. So I get x is greater than or equal to negative 5. And so what these two things are telling me is that on a number line, if I get negative 5 and I get positive 1 on here, I'm going to have an open circle at 1 because that's not included. We cannot equal 1. At negative 5, that's totally fine. If I plug in a negative 5, I get negative 5 plus 5, which is 0. Square root of 0 is 0. That's fine. It's not a negative number, so we're good. It's saying, hey, my x values, they have to be greater than negative 5, but they can't equal positive 1. But everything else that is greater than negative 5 works for us. And so if we're writing this as an interval, we'll just go ahead and read our number line. And so the place where our first part of our interval starts is at negative 5. And then if I follow along my number line, I have to stop at a positive 1. Because I have a closed circle at negative 5, I'm going to use a bracket. That means it's included. Open circle at 1 means I'm using a parenthesis because it's not included. And then I see I have one more interval that's starting at 1 and going towards my big fat arrow pointing to the right, which is positive infinity. And then both of those are going to have parentheses because neither of them are included. And so this interval, along with my number line, is my domain. Let's have you try an example on your own. All right, team, last type of problems. Determine if the following functions are even, odd, or neither. So we're looking at example A. This function was given to us in the form of an algebraic function. F of x equals x cubed plus 4. Whenever I am given a function like this, the thing I want to pay attention to is my exponents. Reminder that if I have a constant, which I have this plus 4, I always need to write in my x to the 0 because that exponent of 0 matters for me. I'm going to treat that 0 as an even exponent. And so if I'm looking at every single exponent, this first one is a 3, which is odd. This second one is a 0, which we consider even. And so I'm going to say, hey, this is neither even nor odd because, and that's B/C, because there is a mix of even and odd exponents. Nice, and that justification is very important. Let's talk about example B. This function is given to me in the form of a graph, which means I'm going to be looking at symmetry. What I notice is that none of this graph that I can see is on the other side of the y-axis, so I don't have y-axis symmetry. I also see that if I spin this graph around the origin, I turn this graph upside down, I'm not going to have the exact same graph that I started with. Because I don't have any symmetry that we learned about, y-axis or rotational, I'm going to say, hey, this function, again, is neither. My justification, because there's no y-axis symmetry and there's no rotational symmetry. This last example, if I'm looking at my function in the form of a table, I'm trying to pay attention to are x values changing sign, y values, or both. Notice for this function is that both my x's and y's are changing signs, so I'm going to have an odd function.